Welcome to Station Production Sailing. In this station, we focus on shop floor operations that assign machines to do specific tasks based on particular sequence. In our textbook, another case study tells a story of Mark, who explains the general setup of a simple one machine scheduling challenge in a manufacturing environment. We can see the figure in our current slide. If we look at the figure, for 3 jobs to be processed by 2 machines, there are 36 variants of jobs sequences. For 6 jobs and 4 machines, there are more than 2 billion variants. Therefore, finding an optimal sequence is a huge task, and a feasible approach in machine scheduling is to apply heuristic. The objectives of machine scheduling is to minimize lead times that consist of all the processing time, setup time, waiting time, laying time, and transportation time. Obviously, minimizing lead times need a production floor to minimize make span. Make span associated with a job processing sequence that is defined as the length of the period that starts with the release of the first job and that ends with the completion of the last job in the particular sequence S. Reducing waiting time in a queue means minimizing idle time that at the same time maximizes machine capacity utilization. Therefore, the production flow can minimize production delay and at the same time work in process inventory to meet due dates. Let's take a look at the flowchart in the current slide on how to deploy company objective based on a set of constraints. From master production planning that consists of MPS or master production schedule and MRP or material requirements planning and MRP2 that is manufacturing resource planning, the company objective is to translate into time objectives that consist of lead time minimization, delay minimization, and capacity utilization maximization. The task of production scheduler is to find a trade-off across those 3 time objectives. Just imagine that you are in a supermarket on a Tuesday morning. Probably you will be the only person there at this time, so you will not have to wait anywhere and will exit the supermarket in a short time. The time of your shopping will be short, but what about the supermarket? If you are the only customer, their capacity utilization is very low. The same effect can be encountered in manufacturing and service systems in regard to customer order lead times and resource capacity utilization. This typical trade-off in scheduling is called the scheduling dilemma. According to the scheduling dilemma, we cannot achieve a reduction in lead time and an increase in capacity utilization at the same time. A case study in our textbook gives an example. Students at Berlin School of Economics and Law arrive at the subway station Berliner Straße, which is about 10 minutes walk from university. They can also use bus 104 to get to the school from the subway station. Assume that the buses runs every 10 minutes and every minute one student comes to the bus stop. In this case, the waiting time and the lead times will be quite long but the bus will take 10 students and have good capacity utilization. Should the buses run every minute, the lead times would be very short, or maybe no waiting time, but the capacity utilization of each bus would be low. In machine scheduling, the basic problem is to determine job processing sequence that determines the schedule of the machine. In the figure in our current slide, there is a machine that is able to process one manufacturing task at a time. A manufacturing task is part of a customer order. All received and orders are collected in the order of job backlog. At a specific time, all jobs are prepared for fulfillment. Fulfilling a job means using the machine to execute the manufacturing tasks requested by customers that are associated with a job. All jobs from the job backlog are ordered, and jobs from the backlog are consecutively processed by the machine in the order determined by the job sequence, in this case order number 1 O1, order number 2 O2, and so on until order number n. The executed tasks create the asset A1, A2 until AN requested by the customer, that is the final products. The basic decision problem associated with the outlined machine scheduling scenario is to determine the job processing sequence that determines the schedule of the M machines. In order to devise the planning objectives in machine scheduling, there are several commonly used performance indicators. For instance, here we have due date DI of job I, that is, determines the latest allowed completion time associated with a job. We have also processing or flow time or PI, which is the time needed to process job job I on the machine. And then release time TI of job I is used to characterize a job that the release time is the time at which the job is completely specified so that its processing can be started. There are three time-oriented objectives. First, completion time. Second, flow time and lead times. The completion time of job I determines the time when a job is completely fulfilled. For instance, it is a time when a job leaves the machine or production system if there is more than one machine. The completion time is denoted as CI. Second, the flow time or FI of a job I is the difference between the completion time CI and the release time RI of a job I. Lastly, lead time is composed of processing time, setup time, waiting time, laying time, and transportation time. Completion times, flow times, and lead times are performance indicators for quantifying the scheduling decisions from the perspective of an individual request. The objectives of scheduling problem is to minimize lateness or tardiness (TDI) of a job I. Job lateness or tardiness measures the amount of time in excess of the due date associated with the job's work-in-process inventory and capacity utilization. The scheduling problem consists of several decision variables as follows. First, lead times is composed of processing time, setup time, waiting time, laying time, and transportation time. Setup time is needed to prepare the machine for processing the next job. Laying time is needed because of some technology restrictions, for instance drying. Transportation time reflects the physical movement of jobs through the machines. And finally, waiting time exists because a job cannot be processed at the next machine since the machine is occupied on another job. Even the waiting time and partially the setup time can be affected by sequencing. In order to evaluate the quality of a job completion processing sequence, and then additional performance indicators are used. First, the make span or MS associated with the job processing sequence S is defined as the length of the period that starts with the release of the first job and that ends with the completion of the last job in the sequence S. Second, average completion time or ACT for sequence S associated with sequence S as the average value of the completion time of the processes jobs if the jobs are processed in the sequence S by the machine. Finally, the maximal completion time or MCT S is the maximal value observed among all completion times after the application of the job. If we look at this slide, lead time is competitive advantage because it can be optimized by optimizing one or more times objectives that compose the lead times, from raw material delivery lead times to final product delivery lead time. A strategy that can distinguish one and other companies is a capability to optimally sequence the task to further reduce production waiting time. In machine-related performance, two indicators can be used. One is capacity utilization as a ratio of actually used capacity and maximum capacity, and average number of jobs or work in progress inventory as a ratio of total flow time and make span. The objective of measuring capacity utilization and average number of jobs is to control idle time not over the allowable limits. In this slide, we can see that a higher number of waiting orders tends to increase lead times, and automatically a machine needs to steadily increase its utilization. However, whenever the maximum utilization is achieved, lead times is still increasing due to longer waiting time in a production queue and thus also higher number of waiting orders. There are two problems in short-term scheduling: assignment and sequencing. For assignment problems, the objective is to optimally assign a machine to a particular job at an appropriate time. Solution procedure is integer programming because the problem is combinatorial and therefore some solution methods can be chosen from branch and bound, heuristics, or Hungarian method. For sequencing problem, the objective is to optimally find order the jobs should be processed on the machines. The solution procedures include Johnson algorithm, Archer's method. Among others, examples of solution procedure are priority rules and genetic algorithm that find optimal order to process a job in several available machines. In our slide, we can see that improved scheduling is capable of reducing make span of the entire production processes from two machines. The make span reduction comes from eliminating idle time and resequencing jobs at both machines, and therefore too early completion or delayed completion can be avoided. There are several multi-machine setups. For instance, in a two-machine flow shops problem, all jobs from the job backlog are ordered and jobs from the backlog are consecutively processed by the machine in the order determined by the job sequence O1, O2 up to ON. O stands for order. The executed tasks create the assets A1, A2 to AN requested by the customers. The basic decision problem associated with the outlined machine scheduling scenario is to determine the job processing sequence that determines the schedule of the M machines. In the current slide, each job requires two production steps. In the first step, the workpiece is printed, and in the second step, the printed piece is protected by a coating. Of course, it is necessary that painting precedes coating for all jobs. An approach to solve the previous slide scheduling problem is by using Johnson's algorithm. This algorithm follows the principle to keep the idle times of the second machine as short as possible. This is achieved by starting those jobs first on the first machine with the shortest processing time at T'(I) machine, and can be machine 1 or machine 2. These jobs are quickly processed by the first machine and then forwarded to the second machine in order to avoid idle times on the last mentioned machine. The starting sequences of the jobs on the two machines should be kept unchanged. Therefore, it is sufficient to define the job processing sequence only for the first machine. The determined sequence then also applies for the second machine. Each job I is characterized by the two processing times Ti prime for both machines number 1 and number 2. The Johnson algorithm starts with splitting up the job backlog into two subsets J1 and J2. All jobs I whose processing times Ti prime for machine 1 for painting are shorter than the processing times Ti prime for machine 2 for coating are put into J number 1 or J1. The remaining jobs are collected in the sets J2. In the second step, both sets are ordered. The set J1 is sorted by increasing processing time Ti prime for machine number 1 for painting, and the set J2 is sorted by decreasing processing time Ti prime for machine number 2 or coating. Let's work with the example in the current slide. The two stations 1 and 2 process 5 jobs, 1 to 5. Each job has different processing time Ti prime for each machine number 1 and number 2. We can see that set jobs 1 or J1 includes jobs number 1 and 4 because in both jobs, processing times for station 1 is shorter than station number 2. So here, if right here 1 and 4, here 1 is lower than 4, here also 3 is lower than 8, and therefore we take 1 and 4, jobs number 1 and 4 all together and make sets J1. For other jobs, we have station number 1 has longer processing time as compared to station number 2, and therefore we have set J2 whenever T for T1 is higher than T2. Here T1 is lower than T number 2, okay? And then for set 1, for instance, meaning that the job sequence will be job 1 and followed by job number 3, because job 1 needs shorter period to complete. And also for set number 2, we have the reverse situation. The sequence is from 3, 5 and 2 because job 3 takes the longest period to complete. Using this strategy, we can minimize idle time due to waiting the second processing time, in this case painting, right? So the sequence here is 1, 1 and then 4, because here 1 is less than 3. Here we have 1, here we have 3. We have 1, here we have 3. But for J2, we reverse the rule, starting from the longest processing time. Here, the longest is at jobs number 3, right? We have here 9. Oh, we have here 7. And then jobs number 5, 4, and finally 1. Okay? And therefore, by combining J1 and J2, we have the first sequence is 1, and then 4, and then 3, and then 5, and then 2. Okay? Additionally, if we have more machine, for example 3 machines, when the maximum processing time at machine number 2 or station number 2 is equal or lower than minimum processing time at machine number 1 or station number 1, then we can add processing time of machines number 1 and 2, and also for machines number 2 and 3. Then we do the same procedure as to machine scheduling. The second example is given in the current slide to compare first come first served or FCFS strategy versus Johnson rule. In the table of the current slide, each job I, paint and coating duration is given. And the lower chart shows machining time using FCFS compared to Johnson rule in the upper table, and we can see that Johnson rule provides shorter production time than FCFS. Another method of job scheduling is priority rules. This is the most intuitive approach for the determination of the job processing sequence to process the jobs in the sequence of their arrival or release times. In the upper table, we have 8 jobs with different release time, duration, and due date. And the release time stands for the time where the jobs sent to a particular machine to be processed. And duration is the machining time for each job. And the due date is that the maximum time need to be followed by an operations manager to complete a particular job I. For instance, jobs number 1. It is the first to be released. So the release time is number 1. And it takes 4 minutes to be processed by machine. And the due date will be at minute number 14, right? Also for other jobs, we do the same. Next, we transfer information from the upper table to the lower table as follows. Release time goes here, duration goes here, and due date goes to this column. Alright? So the first start time according to FIFO rule for job number 1 is at minute or hour number 8. And then we can conclude before hour or minutes number 8 there is no any activities in machining department. Okay, so this will be our start time for the entire jobs. And we can start calculating the finish time because the duration is 4 minutes or 4 hours, and therefore the finish time will be 4 plus 8, right? 4 plus 8 equal to 12. Alright? Similarly here, 12 plus 2 equal to 14. 14 plus 3 equal to 17. 17 plus 7 equal to 24. 24 plus 7 equal to 31. 31 plus 2 equal to 33, and so on until we come to jobs number 8 that the finish time is at minutes or hour number 44. Alright? And according to this calculation, we can just compare between finish time and due date. Then I will erase these arrows, and then we can get cleaner table and columns, and we can compare. For instance, here finish time for jobs number 1 is at minutes number 12, and the due date is at minutes number 14. Okay, let's say our time units is in minute, right? Because due date is higher than finish time, no tardiness. And also here, same for job number 2. 29 is higher than 14, no tardiness. But there is tardiness because at jobs number 3, the due date is lower than the finish time. And then we have 1 here. Similarly here, for due date 23, but the finish time is at minute 31, and therefore the tardiness is 8 minutes, because 31 minus 23 equal to 8, right? Because of this tardiness, and then there is a delay. For instance, jobs number 1, no tardiness, no delay. But jobs number 3, there is a delay, alright? Also for jobs number 5, 6, 7, and 8. Okay? The lead time is, however, a margin between finish time and what? We have here finish time and the release time here. 1, 11. Here 14 and 2. We have 12. Here we have 17 and 3. We have 14. Yeah, we have 14. 24 minus 4, you have 20. And finally, for instance here, 44 minus 8, we have 36. So the lead time for job number 8 is 36 minutes. And the finish time is at 36 for plus the start time of job number 1, the earliest job, equal to 44. It is equal to 8 plus 36. So equal to this and this. 8 plus 36 equal to 44. So this is the total lead times for 8 jobs. Alright. Now we compare with other rule. Here we have SPT, that is shortest processing time. We do the same, transferring all information from the upper table to the lower table. Release time, duration, and due date, right? We also have the same start time. The lower table has some mistakes because actually if we compare and with the number in upper and the lower table, they are not the same. Yeah, for instance, the duration for jobs number 4 is at 7, it is correct, but for jobs number 8, it should be at 4, but in the lower table it is written at 3, and therefore because of this mistake we have to compose a new table that I have prepared here. And then using SPT or shortest processing time rule, I rewritten the previous table, and therefore based on shortest processing time, the shortest job processing time is for jobs number 2, and a job number 5, number 2 we have 2, number 5 we have 2, number 3 we have 3, number 7 we have 3, number 1, job number 1, we have 4, job number 8, we have 4, job number 4, we have 7, and job number 6, we have 8. It is matched with the upper table. Yeah. And then we calculate the due date. The due date actually is taken from the upper table here, right? This is the due date. We transfer the due date also to this table. And then the start time is the same at minutes 8, and the finish time for job number 2 is at minute 10. It comes from 2 plus start time 8, and then the start time for job number 5, that is the second job to be processed, is equal to the finish time of job number 2, right? That is 10. 10 plus the duration, that is 2. 10 plus 2 equal to 12. 12 move here. 12 plus 3 equal to 15. And then 15 plus 3 equal to 18. Here 15 plus 15 plus 3 equal to 18, right? 18 plus 4 equal to 22. Similarly, we check the tardiness here, because the finish time of job number 2 is still less than the due date and no tardiness. But if we look at jobs number 1, the finish time is at minutes number 22. Obviously, it is longer than the due date. It is later than the due date at minutes 14, and therefore there are tardiness at 8 minutes. And also for jobs number 8, number 4, and number 6. However, if we compare this table with another table using FIFO, we can see that the reduction about the tardiness, alright? And the lead time here is calculated. For instance, 8 is coming from here, so it is coming from this here, the starting time, right? And then finish time, so 10 minus the release time equal to 8. Similar here for jobs, the second job, that is job number 5, 12 minus 6, the release time equal to 6. Also for the third job, that is job number 3, it is 15, the finish time minus the release time equal to 12. That is the lead time. And we have information here that the lead times for the last job, that is jobs number 6, at minutes 34. If we compare with the previous, it is at minute 36. Therefore, there is a reduction as much as 2 minutes. So that's explain why shortest processing time is better than FIFO rule. Okay? In the final slide of today's lecture, we will have job shop scheduling. The characteristic of low volume system or job shops are considerably different for those of high and intermediate volume systems. Products are made to order, and orders usually differ considerably in terms of processing requirements, materials needed, processing time, and processing sequence and setups. Because of these circumstances, job shop scheduling is usually fairly complex. This is compounded by the impossibility of establishing firm schedules prior to receiving the actual job orders. Job shop processing gives rise to two basic issues for schedulers: how to distribute the workload among work centers and what job processing sequence to use. In front of us, we have two tables regarding machine sequence and processing times. The upper table showing the machine sequence, for instance, job number 1 need first to be processed by machine number 2, and then machine number 1 and machine number 3. And job number 2 need to be processed firstly by machine number 2, and then machine number 3 and machine number 1. Job number 3 firstly needed to be processed by machine number 1, and then 2, and finally 3. For each sequence, each job has different processing times. For instance, for the first sequence, for job number 1, needs 20 minutes or 20 hours depending on the time unit. For the second, for job number 1, takes 10 minutes, and for the third or last sequence, job number 1 takes 30 minutes and also employs for job number 2 and job number 3. In this case, we would like to employ shortest processing time procedure to find optimal sequence for 3 jobs processed by using 3 machines I equal to 1, 2, and 3. First, we would like to do with iteration number 1. In iteration number 1, we move all number for jobs number 1, that is first processed by machine number 2, and then job number 2 first processed by machine also number 2, and job number 3 first processed by machine number 1. Okay, and for each machine, for instance, job number 1 needs 10 minutes to complete, and jobs number 2 40 minutes, and job number 3 30 minutes, because it used different machine. The first two use machine number 2, but jobs number 3 uses machine number 1. And then we start doing a ranking based on shortest processing time, and therefore job number 1 is ranked first, and then job number 3 ranked the second, and finally job number 2. Alright, and we do the same also for the second iteration. Now we move from the first column to the second column. Right, in the second column, we have also job number 1 processed by machine number 1, job number 2 processed by machine number 3, and job number 3 processed by machine number 1, and we move all of these numbers into the second iteration, the first column of the second iteration. 1, 3, and then 2. For job number 1, for instance, need 20 minutes to be processed by machine number 1. And what about job number 2? To be processed by machine number 3, and it needs 20 minutes. Also the same for job number 3, needs 50 minutes to be processed by machine number 2. And therefore, the first rank goes for job number 1, and the second rank goes for job number 2, and finally job number 3 is the lowest rank. And the third iteration, now we go to the last column in the upper left table, and we again write job number 1 must processed by machine number 3, job number 2 processed by machine number 1, and job number 3 again processed by machine number 3. And then we check the processing time from the lower table, and we have for job number 1 processed by machine number 3 takes 30 minutes, job number 2 processed by machine number 1 takes 15 minutes, and job number 3 processed by machine number 3 needs 25 minutes, and we do ranking The first rank goes for job number 2 because it is the shortest processing time. And then second rank goes to job number 3 because it needs 25 minutes to process the job by using machine number 3. Okay, and finally job number 1 needs 30 minutes to be processed by machine number 3. Okay, after we have a ranking based on shortest processing time for each job at each iteration, and then we start working with our Gantt chart. After we complete our SPT table, and then we transfer the information in our SPT table into our Gantt chart. For the first bar that we would like to put into our Gantt chart is job number 1 at 10 minutes to be processed by machine number 2. And then the next sequence will be job number 2 to be processed by the same machine, that is machine number 2 at 40 minutes. And so the total processing time so far is at 50 minutes. Job number 3 is supposed to be processed after job number 1. However, because both jobs are processed by different machine, and therefore job number 3 can be simultaneously processed with job number 1 by using different machine, in this case machine number 1. So red stands for machine number 1. Alright. The next is that we go for the second sequence. In the second sequence, we know that job number 2 takes 20 minutes to be processed by machine number 3. So it processed after completing jobs number 2 to be processed by machine number 2 at 40 minutes. And then we back to the next sequence of second iteration, that is jobs number 1 processed by machine number 1. So it takes 20 minutes. And therefore, so far, for machine number 1 has processed job number 3 and number 1 at 30 plus 20 equal to 50 minutes. And next, we continue with bar for jobs number 3 to be processed by machine number 2 at 50 minutes, and therefore the total processing time for machine number 2 is at 100 minutes. If we look at the Gantt chart, the next red bar is the last assignment for machine number 1. That is assignment to process job number 2. So what jobs that are left? They are jobs number 3 and 2 to be processed by machine number 3. Machine number 3 is colored by green, right? And then we start calculating lead times for job number 1. That is equal to 100. So where it comes from? It comes from here. First, we put processing time in each bar in our Gantt chart. For instance, for this bar, we have 10, that is job number 1 to be processed by machine number 2. And then we have here, the next is 40. I think I have to put, and here we have 50. Right? And then for machine number 1, first we have 30 here, and then we have 20, and we have 15. Right? And for the green, that is machine number 3, first we have 20, and then here we have 30 here. It is 20, we have 30 here, and therefore 20 plus 30 equal to 1, to 50, and then we have here 25. Alright? Okay, good. Using these numbers, we can calculate lead time for each jobs involved in this process. For instance, job number 1, the lead time is at 100. It comes from here. It is for job number 1. It ends at 100. And jobs number 2, it is from here 10 plus 40 plus 20 plus 15, and therefore equal to 85, right? And job number 3, 50 plus 50, it is 100 plus 125, and therefore we have 125 here, all right? So in total, if we compare job number 1, 2, and 3, which one is the longest? Obviously, job number 3 at 125. Now we go to calculate the waiting time. For job number 1, the waiting time is at 40. It comes from here. Here is 20. Here also 20. Right? Because we have 50 minus 20 minus 10 equal to 20. Also here, 50, because 100 minus 50. 50 minus 30 equal to 20. And therefore we have 40 here. And jobs number 2, only 10 coming from here. It is 10, waiting time. And what about job number 3? It is 20, comes from here. It is 20. All right? So the total waiting time for jobs number 1 and 2 and 3 equal to 70. All right? That is the total waiting time. So now what about the delay? Because the lead time is 150, and therefore there is no delay, and therefore we put here with under bracket, meaning that there is no delay, but it is the jobs for the processing time for job number 1 is earlier than, meaning that the processing time, the actual processing time for job number 1 is shorter than the due date. And what about the job number 2? 85. Actually, the due date is at 80, and therefore 5 minutes late, and the delay is at 5. And what about jobs number 3? Also 5 minutes delay. So in total, there is a delay at 10 minutes. All right? Okay, that's end of our session today for job scheduling, and see you in the next session in week number 12.